Welcome back to TalkTensors, where we take those complex machine learning papers and we break them down into bite-sized insights.
Yeah.
Today we're diving into correctness learning, deductive verification guided learning for human-AI collaboration.
Ooh, that's a mouthful.
It is a mouthful, and it's a really fascinating concept. Imagine self-driving cars making not just decisions, but like the right decisions every time.
Yep.
This paper is proposing a new method for training AI in these complex decision-making tasks where safety is so important and we need to guarantee that the AI is aligning with human judgment and safety standards.
It's a really ambitious goal trying to bridge the power of AI and the rigor of formal verification methods.
Yeah, absolutely. And that's what we're going to be unpacking today in our deep dive. How does this new approach work, and what could it mean for the future of reliable AI?
Right.
So to set the stage, I think we should start with like the elephant in the room.
Okay.
What does correctness even mean when we're talking about AI?
Right.
Especially in these situations where safety is paramount, like a self-driving car.
Yeah. That's the crux of the issue, isn't it? You have these incredibly powerful AI systems trained on mountains and mountains of data, capable of making split-second decisions. But how do we actually ensure that those decisions are going to align with what a human expert would deem correct, particularly in these dynamic environments?
Yeah.
I mean, think about it.
Yeah.
Current methods often rely on human feedback, which, let's be honest, can be pretty subjective.
Totally.
And inconsistent.
Yeah.
This paper's arguing that we need a more rigorous approach, like we need something that's provable, something we can rely on.
So enter correctness learning, or CL as they call it.
Yeah.
What is the core idea here?
So CL aims to formally verify the correctness of the AI's decisions using mathematical methods.
Okay.
It's about creating this symbolic representation of how the AI executes instructions, setting a benchmark for its actions, and then using deductive verification.
Okay.
So this is a logic-based approach to actually prove that those actions are correct.
So instead of just saying like, hey, AI, try not to crash the car, we're giving it a set of rules to follow.
Yes. Provable logical rules to follow.
And it has to operate within those rules.
Exactly. And what I find really fascinating is that they're taking inspiration from proven successful schemes, and they're identifying these patterns of behavior that consistently lead to correct outcomes.
Okay.
They call this pattern-driven correctness learning, or PDCL.
PDCL.
Yeah, it's a lot of acronyms, I know. But bear with me. It's about injecting this correctness pattern into the AI training process.
Oh, so it's almost like we're trying to get the AI to learn from the best?
Yeah.
Like if we understand what makes human experts successful in a certain task, we can teach those principles to the AI.
Exactly.
Okay, so to make this a little bit more concrete for our listeners, can you give us a specific example of a problem that this paper tackles?
Sure. So they focus on what's called job scheduling, which is a classic computer science problem where you have a set of tasks, you have limited resources, and the goal is to figure out the most efficient way to allocate and schedule those resources.
Yeah, like optimizing routes for a fleet of delivery trucks.
Exactly. Or managing tasks in a complex manufacturing process.
So they're training an AI to be a super efficient scheduler.
That's it. That's the goal. And in job scheduling, correctness is very clearly defined, right? It's about finding the most efficient solution that meets all the constraints.
Makes sense.
And they use historical data from expert human schedulers to actually extract those correctness patterns.
Interesting. So the AI isn't just copying what the human did, it's actually extracting the general principles from what the human has done to apply to new scheduling scenarios that it may encounter.
Precisely.
So walk us through how they actually practically implement this pattern-driven correctness learning. They mentioned this two-layer approach, right?
They do. So they divide this job scheduling problem into two layers.
Okay.
The upper layer focuses on high-level decisions, like think of it as like a project manager prioritizing tasks.
Okay.
And then the lower layer handles the resource allocation, making sure that those tasks are executed as efficiently as possible.
Right. So it's like you have the strategic planning layer and then you have the tactical execution layer.
Yeah, that's a great way to put it.
How do they ensure that these layers work together while also adhering to those correctness patterns that we've been talking about?
That's where the magic happens. They use a combination of reinforcement learning, which is a technique for training AI to make sequential decisions.
Okay.
And then the deductive verification that we talked about earlier. So the upper layer using reinforcement learning receives rewards not just for coming up with an efficient schedule, but also for aligning its decisions with those correctness patterns.
So the AI gets like bonus points.
Yes.
if it makes a decision that sort of matches expert human behavior.
Exactly. It's encouraged to move away from solutions that might be technically feasible, but not as efficient as what a human expert might choose.
Yeah.
The lower layer also uses reinforcement learning, and it receives real-time feedback from that upper layer.
Okay.
Constantly adjusting its resource allocation strategy to make sure that the upper layer's decisions are executed as efficiently as possible.
So there's this like very carefully choreographed dance between those two layers.
Yes, very much so.
What kind of tools are they using to make this happen? I mean, you've mentioned deductive verification, you've mentioned reinforcement learning, but are there like specific software platforms that are involved?
That's a great question, and one that we will dig into next time.
Okay.
But for now, we'll leave you to ponder the implications of an AI that can demonstrably make correct and perhaps even better decisions than human experts.
That is quite a thought to ponder.
It is.
Okay, so tune in next time for part 2 of our deep dive on correctness learning.
We'll be back.
We'll see you then.
Welcome back to TalkTensors. Last time we were talking about this research group tackling the challenge of correctness in AI, using this clever 2-layer system of reinforcement learning. And
you're right, we kind of left off without really talking about like what platform they're using to build it.
Right. It wasn't just a theoretical exercise.
Yeah.
They really got into the nuts and bolts of like, how do we actually implement this?
Right. I'm dying to know, like, how did they build this system?
Well, they used a combination of existing tools and techniques for the reinforcement learning part. They relied on some popular open source libraries. But what I found really fascinating was their use of a tool called Coq.
Coq, that does sound familiar. I think we talked about that in an episode about formally verifying the Cello for microkernel. It's like a mathematical proof assistant, right?
You have a great memory. Coq is an incredibly powerful tool for formally verifying the correctness of software systems. It's been used to prove everything from the correctness of complex algorithms to the security of operating systems. And in this paper, they use Coq to formally model the job scheduling system and prove the correctness of those correctness patterns extracted from the historical data.
So they're like building a house on a solid foundation of concrete instead of sand, you know?
Yeah.
They're using Coq to like establish this bedrock of mathematical certainty and then letting the AI loose to learn and explore within those boundaries.
That's a great analogy. And that's what makes this approach so compelling. It's not just about training AI to be good at a task. It's about training it to be good in a way that is both understandable and trustworthy. As we rely more and more on these AI systems for critical tasks, we need to be sure that those systems are making decisions based on sound logic and principles, not just statistical correlations or lucky guesses.
So they're using Coq to like keep the AI honest, making sure it's not like cutting corners or coming up with solutions that might be technically feasible but ultimately unsafe or unreliable.
Exactly. And here's a really cool detail about how they use Coq. They didn't just use it to verify the high-level correctness patterns. They actually used it to analyze the AI's decision-making process step by step.
Hold on. So they're like watching the AI, I think, in real time.
Yeah.
Like peeking inside its artificial brain and seeing how it's arriving at its decisions?
In a way, yes. And what's even more remarkable is they were able to identify these emergent patterns in the AI's behavior that weren't explicitly programmed in things like how the AI would prioritize resources under different conditions, or how it would adapt its strategy based on the changing state of the system. It was as if the AI was developing its own internal logic, its own way of understanding the problem.
So it wasn't just following the rules, it was learning to play the game at a deeper level.
Exactly. And because they were using Coq, they were able to observe and understand that emerging internal logic in a way that wouldn't have been possible with traditional black box AI training methods.
That's pretty wild.
It is.
It also seems like a really valuable tool for just understanding how these complex AI systems actually work.
It is.
But let's get back to the practical side of things. You mentioned that they tested this approach against some standard scheduling algorithms. What kind of performance improvements did they actually see?
The results were pretty remarkable. Their approach consistently outperformed the traditional methods, often by a substantial margin.
They saw significant improvements in both the time it took to complete the tasks and the amount of resources used.
Wow, so we're not talking about just like a small percentage point increase in efficiency. This was a real leap forward.
This is a big jump.
Okay, so this wasn't just a theoretical exercise.
Yeah.
They were able to show that this approach could actually lead to tangible real-world benefits in terms of time and resource optimization.
I can see why you're so excited about this paper, but Were there any limitations to their approach, anything that they identified as an area for future research?
You always ask the best questions.
Yeah.
Yes, they were very upfront about the limitations. One key point they emphasized was that the correctness patterns they extracted from the historical data were very specific to the particular job scheduling problem they were studying.
Uh-huh.
So if you were to apply this approach to a different scheduling problem, say scheduling flights at an airport,
Right.
you would need to start with a new set of historical data
Okay.
and extract a new set of correctness patterns relevant to that specific domain.
That makes sense. Scheduling workers in a factory and scheduling flights at an airport are two very different beasts, each with their own unique set of constraints and complexities.
Right. You can't just assume that the rules of one game will automatically apply to the other.
Right.
But what's really exciting is that the underlying framework they developed, this idea of using deductive verification to guide reinforcement learning, is incredibly generalizable. It could potentially be applied to a wide range of decision-making problems, as long as you can clearly define what correctness means in that specific context.
Okay.
And find a way to extract those relevant correctness patterns from data.
So it sounds like they've created this incredibly powerful new toolkit for building reliable, trustworthy AI systems.
I think so.
And now it's up to other researchers and engineers to take those tools and run with them, applying them to all sorts of new and exciting challenges.
Exactly.
But before we get too carried away dreaming about the future of AI, I think it's time for us to shift gears and get to our novel notions segment.
I always love this part. Let's do it. Welcome back to TalkTensors.
It's time for our novel notions segment, where we take the ideas from the paper and stretch our imaginations a little bit.
I'm always ready for some mental gymnastics.
So we've been deep diving into correctness learning, where we're essentially trying to bake the concept of correctness into AI systems from the ground up.
Using those correctness patterns extracted from expert human behavior.
Right, but here's my thought. What if those patterns are just a starting point? What if instead of treating them as fixed and immutable, we start thinking about how AI could contribute to the evolution of correctness itself?
Wow, you're going meta on me.
You're suggesting that AI could help us redefine what correctness even means.
Exactly. Imagine AI systems that, as they learn and solve problems, they identify even better, more efficient, or more nuanced ways to achieve correctness. It's like a feedback loop with AI pushing the boundaries of what we consider correct in a given domain.
That's a bold idea. Instead of just mimicking human expertise, AI would actively contribute to the growth of that expertise, almost like having an AI research partner constantly challenging our assumptions and expanding our understanding. Think about the implications for fields like science and engineering. We could have AI systems helping design better algorithms, discover new scientific principles, or even compose groundbreaking music, all by exploring new frontiers within these evolving correctness landscapes.
That's a fantastic image, these dynamic landscapes where AI not only navigates but reshapes the terrain of correctness itself. But hold on, there are some serious questions that come with this level of AI autonomy. How do we ensure these systems remain aligned with our values? How do we prevent them from optimizing for correctness in ways that might be technically sound but ethically problematic?
You're hitting on the core of responsible AI development. As we give these systems more freedom to define and pursue correctness, we absolutely need robust ethical frameworks and oversight mechanisms. It's a challenge that will require collaboration between AI researchers, ethicists, social scientists, and policymakers.
It's a tall order, but I think the potential benefits of this kind of human-AI partnership are too significant to ignore. We could be on the cusp of a new era of discovery and innovation where AI helps us solve problems we couldn't even fathom on our own.
And that, my friends, is why we love diving into these cutting-edge research papers. They not only give us a glimpse into the future of AI, but they also force us to grapple with these profound questions about our evolving relationship with technology.
It's a reminder that AI is ultimately a reflection of ourselves, our values, and our aspirations as we build these increasingly powerful systems. It's crucial to have these conversations about the kind of future we want to create, and a reminder about our novel notions segment. These are highly speculative ideas, the bleeding edge of what might be possible.
That's right. Don't go building your AI research partner just yet, but we hope these discussions spark your imagination and inspire you to think about the possibilities.
If you have any novel notions of your own, we'd love to hear them. Share your thoughts on social media or leave a comment on our website.
And be sure to join us next week for another exciting paper and more thought-provoking discussions. Until then, keep those AI synapses firing.